Hey guys, so I'm running this a bit earlier this week. It's mainly just because I ended up having some free time today and I want to use the weekend to study for the midterm. So, last week we looked at how we could use a rootkit to spawn a remote shell by sending a ICMP packet to the infected server with a particular message. So we use go root, and if you sent that, we also could listen on netcat and it would send us the remote shell that we could then do whatever we wanted with. So that was one of the features that I wanted my final rootkit to have for my Something Awesome project. The other was keylogging. And then the rest of the time I was going to spend on getting reboot persistence, so how we could have the rootkit automatically start up. And then the last bit is hiding it. So we wanted to be able to hide processes and be able to hide files. So the textbook has a really cool example of a keylogger, but it's not exactly practical because it just prints everything out to standard out so you can see it on dmessage, and it's pretty easy to tell that there's a keylogger there. So what we're doing instead is we're just going to write it to a file, and then in future weeks we're going to look at how we could potentially hide that file. So today I'm going to go a little bit more through how a standard kernel module looks, and I guess sort of how we can hook system calls to do various nefarious things. So I'm going to start off at the bottom of the file, sort of work my way up. So declare module is just a pretty standard way to just create a module. So it's a macro that will expand out. This struct, again, is just like, I guess, the bookkeeping for the module we've written. So we give it a name. We're also going to look in future how you can hide the existence of it. But right now it's assuming that you're actually wanting to do something that the user knows about. So you give it a nice helpful name that shows what it does. You also need to provide a pointer to the load function. So load is where sort of the entry point for when you load and unload the module from the kernel. So when you call kld load, this bit is run. So we set up a file lock that we'll talk a little bit more about in future. And then we also override the system entry table for our read calls. So instead of calling the sysread function, it will call read hook, which is where we do our little evil stuff. When we unload the module, we want to put the kernel back into the original state. So we just replace it back with that sysread. We also want to destroy the lock we've created. That's sort of a bit of a memory leak at the moment that I've got, and I'll fix that up later. So the read hook itself is really quite simple. So all we do is we have the exact same calling sort of signature that the sysread has. So we get a pointer to the thread that has requested the read, as well as the arguments for the read. So the great thing about FreeBSD is it's an open source operating system. You can go and easily see all of this sort of stuff by just reading the source code. It's changed quite a bit since that textbook that I've been reading came out. So if you're looking at building rootkits for modern FreeBSD, you are going to want to check the source code because some things have changed, and yeah, the textbook is outdated effectively, but still has some really cool information that's applicable to not just FreeBSD, but Linux and Windows operating systems too. So we convert the syscall args, we just cast it as the struct read args. Like I said, you can see what fields this structure has by reading the source code. We set up a error integer, a character buffer, and size. We then call sysread, so we haven't really done anything at this point. We're still just doing the built-in sysread. Then the error returned, we return. So if the sysread fails, we don't want to do anything else because there's nothing we can do. And there's a couple of other extra features that maybe we're interested in too. An example of that is, if the read was for more than 1 byte, or if the read wasn't for standard in, then we don't care about it. So we just return the error. If it was for standard in, then we're going to copy in the string from user space into our kernel buffer, and then we're going to do some extra stuff with it. So in the previous one that the textbook provides you, this is where you then just do printf buffer, and you're done. Instead, what we want to do is we want to write it to a file so that we can use our remote shell exploit to log in and read what keys the users have been pressing. So we go into a little bit more depth. The first thing we do is we gain mutual access on this file log. We don't want multiple processes or threads to be calling this read hook at the same time and writing to the file. So you can think about, like, if you have multiple users typing, you don't want them both to be writing to the file at the same time because it gets gross pretty quick. So what we do instead is we get mutual access to this file lock, then we call kern open. Kern openat is what sysopen eventually calls. Sysopen is a wrapper around kern openat. So this is why it's nice to be able to read the source code, because you'll see that sysopen expects your file path and all of that sort of stuff to be a buffer that lives in user space. So if you don't operating systems, you know it's got to securely copy it into the system space. If you provide a system space buffer to sysopen, it'll panic because it's expecting it to be in user space and copy it across. So what we do instead is we sort of bypass all of the stuff that sysopen does, and we just call kern openat directly. So a lot of these parameters are the same as, open if you're using libc or something like that. We pass our thread to kern openat. We also pass this at fdcwd. So this is if you're giving a relative path, you need to give it relative to another open file so it knows where to go. This is ignored because we have an absolute path, which is going to write this to my home directory. So that first bit is actually ignored. We let it know that we're getting stuff from system space, so it needs to take that into consideration. And then this is just the flags and the mode that you're used to from sysopen. So you open the file in read-write mode, we create it if it doesn't exist, and then we append so that we're at the end of the file. We also just give it 700 for the mode. The next bit is we just build up the arguments that we need to perform a write. So kern openat will put the return value, which is our file descriptor, into this bit. So we set the write args file descriptor to that. We point it to the start of our buffer, and we tell it we want to write 1 byte. We then call the write hook. We then want to give it a /n afterwards. And this is because when I was testing it out before, I didn't have that. And it got quite confusing if you had two terminals open typing, because you'd have one person's commands interlaced with another person's commands on the same line. So here we just do a /n, and then when you're reading it, you'll need to sort of think a little bit about, are key presses coming one after the other, or is it several users typing at the same time? So we do a /n, then we call the write hook, then we close the file, and we release the file log. Our write hook isn't actually hooked up at the moment to the system calls. It could be if we wanted to, but here we're just using it to write to that file. So this is actually the exact same as what syswrite does. So I copied this directly from the operating system. The only difference is, again, syswrite is expecting a buffer from user space. So all we've done is we've taken the exact same code, used it to build up our UIO and IOVEC, and instead we've put segflag to be system space, and then we call kern write v. So that will allow the write to happen. We're ignoring errors at the moment. That's really because if there's an error that happens, there's not a great deal we can do about it, right? It doesn't cause anything to crash, but we don't want to log it because then, it gives the users some hints that there is a rootkit that is trying to do arbitrary writes on their machine. So we just ignore the errors. I did use them originally to help me with debugging. And that's about it. So after this, I'll go through, showing you in action. As you can see how we sort of have no idea that it's actually running. Okay, cool. So we looked at how the source code worked, how our kernel module works, and now I'm just going to finish off with a demonstration. So I've already tested it out a few times. The first thing I'm going to do is I'm just going to remove it. And then we're going to just type some commands in one window and then view it in the other window. So we have a good idea as to what it actually looks like. So on the left, doesn't exist yet. We're going to use sudo kld load. Sorry, first we need to make it. And then we use kld load, keylog.ka. So one of the weaknesses of this right now is I can just type kld stat, and it's going to show me here that it's running, right? So that's one of the other things we're going to be looking at, how we can avoid it in the future. So I'm just going to press some keys like I usually would. Maybe I'm just going to do an ls, maybe I'll do a make clean, maybe I'm going to go up a directory and check what's here, maybe I'm going to come into hello, see what's there. Maybe I'm going to take a look at the make file. Maybe I'm done with that. I'm going to close it. So if we come over to the left now, we should see that we have quite a few key presses here. So if we start up at the top, we can see that we typed in kld stat, and then we pressed enter, and then we pressed ls, and then we pressed enter, and then we pressed make clean and enter. We went up a directory, we did another ls, we did cd, we pressed k, then we pressed delete, and then we pressed hello, and then we did vim makefile, and then we switched over and opened up this file. So you can see it's quite powerful, and you can see me typing in here. It wasn't slow or anything like that, so it would be pretty hard to actually tell if it was running. Like, there's not really much difference. I might run it again, and I need to go back to there. Might run it again, and then we'll just have htop running in the background. So you can see it's not, it's pretty hard to tell that it's running, right? Like, it's not causing the CPU to spike or anything like that. Maybe it does a little bit, but this was a machine with lots of people running on it. It's not something that you would easily tell that was there, so it's quite hard to detect. So that's it. So we've got the keylogger, we've got remote code, or remote shell. So now we're really just going to explore how we can hide the existence of this stuff. So we're going to be taking a look at rootkit hunter, learning a bit about how kernels try to detect if they got rootkits in them, how we can try and evade some of those detections, and have some fun with that. So thanks for watching.